Hi, we are going to look at some theorems about continuous functions and focus a little bit on thinking about continuity based on the equation of the function rather than the graph. Okay, so the first thing I want you to think about is the substitution shortcut theorems we had from when we first started talking about limits. So, for example, if you think about the one for polynomial functions, we have this property that says that if we're taking the limit as x approaches a of a polynomial function, that we can just substitute that value in for x. And so if we think back to that and you think about the definition of continuity that we just started with, this is essentially the definition of what it means to be continuous. So essentially what those theorems that allowed us to use substitution as a shortcut really are saying is those theorems, if we kind of think about them now that we have this vocabulary of continuity, it's saying that polynomial functions are continuous at every value of x. And we had a lot of other substitution shortcut theorems, some of which were for functions that might have restricted domains. And so if we go back and look at all of those, they all have this idea that you can substitute the value into the function to get the limit sometimes, as a shortcut sometimes. And if you think about all of those theorems, essentially all of those theorems are really talking about those functions being continuous on their domain. So that means that when you are working with functions that fall into those categories that we have substitution shortcut theorems for, and you're asked about continuity of those functions, for many of those functions, you're really just thinking about domain. So for example, if you are thinking about a function like f of x equals our polynomial that we had up above, because of that substitution shortcut theorem, it tells you that that function is continuous on its entire domain, which is all real numbers. Or if you think about a function like a rational function, that function also is continuous on its domain, which would be all real numbers except 0. Or if we think about other functions for which we had substitution shortcut theorems, so for example sine and cosine functions, we had substitution shortcut theorems for some transcendental functions, and those functions also are continuous on their domain. So if you think back to when you learned about trig functions and think about the domains, different ones have different domains, but for the sine and cosine function, their domain is all real numbers. So those results really come from those substitution shortcut theorems that we already had from before, just now connecting that to our definition of continuity. Okay, so that's really powerful and provides us lots of ways to check for continuity of functions. There are a few other theorems down here that I want to mention about continuous functions. Some of these we will see again later in the semester and focus on using a little bit later. And some of them you might use, but you're not necessarily realizing that you're using them. This first one talks about inverse functions. So if we know we have a continuous function, and we think about its inverse function, then we also have continuity of inverse functions. So this is useful for things like inverse trig functions. So if I think about the inverse trig function, sine inverse of x, and connect that to the sine function that I just talked about continuity of. So the sine function is continuous on negative infinity to infinity, but its inverse is only defined on a specific interval. We have to restrict the sine function to the interval negative pi over 2 to pi over 2, where it's 1 to 1, to define the inverse function. But I can now use this theorem to think about that the inverse function is going to be continuous on the interval that corresponds to negative pi over 2 to pi over 2 from that inverse function. And the interval negative pi over 2 to pi over 2, right? When x goes from negative pi over 2 to pi over 2, the outputs go from negative 1 to 1. And so we can think about this inverse function that's going to be continuous on that that interval that we're mapped to from -1 to 1. We talked a little bit in the last video about talking about right continuity or left continuity at endpoints of the domain so that we don't have to consider those two-sided limits. So this is an example of a function where we have endpoints of the domain. But this theorem about inverse functions, you may or may not realize you're using it, but you can use that often to sort of connect the theorems we have for substitution shortcut theorems to other functions and think about where they are continuous. This next one, also compositions, allows us to think about composing functions that we already know about. We have a theorem that is essentially just like this, where we looked at the combining functions theorem for composition, and it is exactly the same, really. It's just written in slightly different notation. But that allows you to think about functions like f of x equals sine of, say, x squared plus x, where I've got a polynomial inside a sine function. And so my inner function, x squared plus x, is continuous everywhere, and the sine function is also continuous everywhere. So this function that we're looking at here by this composition theorem is going to be continuous everywhere. So on -infinity to infinity. All right, this last one, we will actually see a little bit more. I think there's one question in your My Math Lab homework about this, but we'll use it later when we look at some other things. So this is something that actually should kind of just make sense if you think about what it's saying. So I'm going to draw a picture out to the side here so we can look at what this theorem is actually saying. It says that we have a continuous function on an interval a to b. So I'm just going to draw a graph here, mark off some values a and b, and I'm going to draw a function that is continuous between those points. So there have to be outputs at a and b, and the function has to be continuous on that interval, so it has to pass through those points and no breaks in the graph. All right, so I just drew an example of a function that is continuous on that interval a to b. I'm going to label a couple other things here on the graph that it talks about in the last part of the theorem. So I have f of a, so that would be the y coordinate of that point where x is equal to a, and f of b. So that is the y coordinate that corresponds to x equals b. All right, so if f is continuous on the interval a to b, and then the other thing it says here is that y naught is any value between f of a and f of b. So I've got this interval here where I can just pick anything in there to label as y naught. So I'm just going to label some value in there as y naught. Then there exists a value x equals c in the interval ab for which f of c equals y naught. And the easiest way I think to understand this theorem is to think about the graph. And so if I draw that line across there at y naught, what that theorem says is that there has to be at least one point in the interval AB. There could be more, but there has to be at least one point in the interval AB where that graph has to pass through the y naught. And that's your value of C. All right, so I saw one time a joke, and maybe I'll post that in our course, that said, why did the chicken cross the road? Answer, the intermediate value theorem. The graph, the chicken, has to cross the road in order to get from this point at x equals a to this point at x equals b. So the chicken has to cross the road. The other thing I guess I want to say about this too, I did mention it as I was talking about it, but there could be more than one point. In this graph that I drew, there's only one point, x equals c. In that interval a to b, there's another point beyond the interval, but only one point in that interval where the function actually crosses that y naught, but there could be more than one. All right, so again, there's just one little short question in your homework about that theorem, but we'll use that later on, so we'll come back and look at that theorem some more later on. All right, last big thing, there's quite a few questions in your homework related to this about determining continuity of a function from the equation. All right, so generally I start thinking about if this is the kind of function that I have substitution shortcut theorems for, and then I go back to think about those. And so often that's really about thinking about the domain. All right, so if you have substitution shortcut theorems for the function that you're working with, really all you need to consider is domain. And so I have several examples written here on this screen, and then we'll look at some more examples in the next video. The polynomial function, this rational function, the sine function, the inverse sine function, and the sine of the polynomial function are all examples where really all I need to think about is domain. So sometimes that's really all you need to consider. Remember that continuity is not really just about domain, but because we have these theorems that connect the limit as x approaches a of f of x to f of a for certain functions, those substitution shortcut theorem functions, then that gives us the power to really just focus on domain for those functions. But there are functions for which that's not the only thing to consider. So the other thing to consider is other places where it might not be just the f of a that fails to exist, but it might be the limit that fails to exist or fails to equal the function value. Okay, so where might those things occur? Those are going to possibly occur where you might have pieces of a graph that do not connect. All right, so one common place that you might see that is when you look at piecewise defined functions. And I'm just going to write a really simple example down here. So this is a piecewise defined function. I've got two pieces here. Both of the pieces are really simple functions, but thinking about that those pieces might not connect when I do that. This one's really easy to just think about the graph. The graph is the function y equals x, so that's just a straight line when x is less than or equal to 0. So it's a line through the origin with slope 1. And then the constant function, f of x equals 4. I'm just going to put a point up here and label it 4 when x is greater than 0. And so you can just visualize what the graph looks like here and realize that those two pieces are not going to connect. Mathematically, what I could think about is which of those two reasons would it be that the limit does not exist, or that the limit exists but it's not equal to f of a. All right, so for this one it's pretty easy to see that the limit as x approaches 0 of f of x does not exist. So this function would be discontinuous at x equals 0 because that limit does not exist. All right, and again, like we talked about in the last video, when I'm thinking about continuity, I usually start by thinking about where a function might fail to be continuous, and then realizing that the function is going to be continuous everywhere else on its domain. So for this example that I have here, this function here is continuous everywhere except at 0. We are really using intervals of x values. We say the function is continuous on that interval, but those are really the inputs for the function. Some of the homework says interval of x values, and sometimes it just says given interval, but it's really always asking about the inputs of the function when it's asking you to state where a function is continuous. All right, the next couple videos have a bunch of examples.